Hi everyone. Think back to when you were in high school doing algebra and pre-calculus. There are a couple of questions that you learned to ask about functions. One question is, what is the range of f? So by definition, the range of f is the set of all values that f of x can be. So for example, the range of sine of x is the interval from -1 to 1, because that is the range of values that sine of x can take. And I'll point out that, in general, solving for the range of a function could be hard. For example, what's the range of e to the x plus x squared? The answer is, well, I don't know. I mean, you can do some work on this and you can make some progress, but you're not going to get a completely satisfactory answer. Anyway, so another question you could ask is, what are the zeros of f? The zeros of f are defined to be the x values such that f of x is equal to 0. So for example, the zeros of sine of x are 0, plus or minus pi, plus or minus 2 pi, all of the multiples of pi, because those are the x values, which when you plug them into sine of x, you get 0. And again, this could be complicated to calculate in general. For example, what are the zeros of e to the x minus sine of x? The answer is, I don't know. So one thing that's worth pointing out in terms of comparing these ideas is that if you think of the function f as a process or a transformation that takes the x values as input and produces the f of x values as output, the range of f naturally lives on the right of this picture because it's the set of all f of x values. Whereas the zeros of f naturally live on the left side of the picture because the zeros of f are defined as x values, and not all x values, but x values that satisfy a certain property, that f of x is equal to 0. Okay, so now suppose t is a linear transformation from Rm to Rn. We could similarly define the range and the zeros of t. But now that we're at a higher level of math, there are actually more sophisticated words for these concepts. So instead of range, the word that's used is image. The image of t is the set of all t of x, so it's a set of all things that you can get as the output of the linear transformation. I'll point out that there are some books and resources that will use the word range for this, so that is a word that's used. And there's another term that's commonly used, which is the column space, and you'll see why this term is used for it in a minute. But the word image, I think, is a little bit evocative when you think of t as a transformation, because it's sort of like you're taking all of the vectors in Rm, in the domain, and you're plugging them into t, and you're seeing what they look like collectively as a set inside of Rn. And so it's like the image, it's like the picture of all of the vectors in the domain after they've been processed through the transformation. And then finally, it's common to abbreviate it to just IM instead of writing out the whole word image. Okay, so on the other side, on the domain side, you've got the zeros of t, but the more fancy term for that is the kernel. So the kernel of t is the set of all x such that t of x is equal to 0. So it is the same thing as the zeros. And I actually looked it up and I couldn't find a good explanation for why the word kernel is used in this context. But it is a widely used term in this context. There's another term that's commonly used, which is the null space. I know it's a lot of words, but this is one of those things where, because linear algebra is such an old subject and it's applied in a lot of different areas, there are different words that are used by different groups of people. So like mathematicians might be more likely to use the terms kernel and image, whereas engineers might be more likely to use the terms null space and column space. If you want to talk to both groups of people, then you have to know all the different words that are used. But anyway, let's move past the vocabulary and let's talk about how you actually calculate these things. We know that if you have a linear transformation, then there's some matrix that corresponds to it. So let's call that matrix A, and then the relationship between t and A is that t of x is equal to A times x for all vectors x. So then, putting that into the definition of the image, we see that the image of t is just the set of all vectors A times x. so it's the set of all things you can get by taking a vector x and multiplying it by a. And then because t and a are so closely related, it's also common to refer to this as the image of a. So to analyze this further, we could look at the columns of a. Then we can expand out a times x using the column picture for how matrices multiply times vectors. And we get x1 times v1 plus x2 times v2, and so on. Well, this is exactly a linear combination of the vectors v1 to vm. This is what linear combination means, that you multiply the vectors by scalars and then add everything together. And so the conclusion is that the image of A is just the set of all linear combinations of the columns of A. Which, by the way, this is why some people refer to it as the column space. So this seems like a nice answer, but as we'll see in the next example, it's not always the best answer. Let's look at this matrix. Because it's a 2 by 2 matrix, we can view it as a transformation from R2 to R2. And we can try to visualize A by looking at what happens when we plug in these standard vectors E1 and E2 and multiply them by A. Well, when you multiply A times E1, you get the first column of A, which is 1, 1. And when you multiply A by E2, you get the second column of A, which is 2, 2. And so the thing is, because these two vectors are pointing in the same direction, when you take combinations of the two vectors, you don't get things that are going in different directions. Everything is going to be on that same line. So based on what we learned earlier, we would say that the image of A consists of linear combinations of 1, 1 and 2, 2. But also, from the geometry, we can see that the image of A is just the set of vectors on that line, which can be described by a single parameter as just scalar multiples of 1, 1. And what's kind of interesting about this is that when you look at scalar multiples of a single vector, you can think of those as being linear combinations of that vector. Because if you just have one vector, the only linear combinations you can make are the scalar multiples. You don't have two different things to add. So we can describe the image of A as being linear combinations of 1, 1. But we can also describe the image of A as being linear combinations of 1, 1 and 2, 2. There's no contradiction there because you end up with the same set of vectors either way. The issue is that when you call it the linear combinations of 1, 1 and 2, 2, that's kind of redundant. It's not the most efficient description. And the reason is that 2, 2 is already a scalar multiple of 1, 1. And so you don't get anything new by throwing in 2, 2 in addition to 1, 1, because you already get 2, 2 as 2 times 1, 1. So what this example shows us is that if you just take the linear combinations of all of the columns of a matrix, you'll get a correct description of the image of A, but you won't necessarily have the most efficient description. And so the question is, how do we find that most efficient description? In this example, we were able to draw pictures and so on. But if you had like a 5 by 7 matrix, then probably you won't be able to draw a picture. And so the question is, how do you algebraically find the most efficient description? So how do you find the most efficient description of the image of a matrix? Well, you'll be pleased to know that the answer is the same thing as everything else in this class, which is Gauss-Jordan elimination. But, as usual, the real question is, how do you use Gauss-Jordan elimination to get the answer? Let's look at an example that's a little bit more interesting than the one we just saw, and see how it works. So if you take this matrix and do Gauss-Jordan elimination on it, then, according to Wolfram alpha, what you get is this. And then, of course, the question is, what does this tell us? What are we supposed to get from this? Well, for the purpose of answering this question about the image of A, what you want to do is focus on the locations of the pivots. In this case, you have a pivot in the first column and then in the second column, but the third column doesn't have a pivot. So my claim is that the third column of A is a linear combination of the first and second columns. And not just in this example, but this is a general phenomenon, that in general, non-pivot columns are linear combinations of the pivot columns. So I'll give some explanation in a second so that you can believe that this is actually true. But once you believe it's true, then this gives us a really easy way to get the most efficient description. You don't use all columns of A, you just use the pivot columns. So the image of A is the set of all linear combinations of the pivot columns of A. And this is actually the most efficient description. So in the above example, we would say that the image of A is the set of linear combinations of 1, 1, 1 and 1, 2, 3. An important point here is that when we talk about the pivot columns, we're talking about the pivot columns in the original matrix A, not in the reduced echelon form. And then because this comes up a lot where you're talking about sets of linear combinations, there's a terminology in shorthand for this, which is called span. So the span of 1, 1, 1 and 1, 2, 3 is, by definition, the set of all linear combinations of 1, 1, 1 and 1, 2, 3. We'll see this term span coming up again and again in different settings, so it's important for you to know it, but this is all there is to know about it. It's just another way of describing the set of all linear combinations of a set of vectors. So, why does this work? This thing where you just take the pivot columns. Why is that the right answer? Well, the reason is that when you do row operations, the relationships between the columns don't change. So like in the above example, you can see in the matrix A that the third column is the sum of the first two columns. When you add column 1 and column 2, you get column 3. And that relationship is still true even when you look at the reduced echelon form. In the reduced echelon form, if you add column 1 and column 2, you get column 3. And that's a phenomenon that always happens. When you do row operations, then if there is some relationship between the columns to begin with, that relationship will still be there after you do the row operations. And the reason for that is that column relationships give solutions to the homogeneous equation AX is equal to 0. And we know that when we do row operations, it's like multiplying by elementary matrices on both sides of the equation, but because the right side of the equation is 0, that side doesn't change. And so the solutions to AX is equal to 0 are the same as the solutions to Rx is equal to 0, where R is the reduced echelon form. Okay, this is a little bit abstract, but let's go through this particular example and see what I mean. So let's let V1, V2, and V3 be the columns of that matrix A. Now the relationship between these columns that we know is that V3 is V1 plus V2. But we could move the V3 to the other side of the equation to write it like this. V1 plus V2 minus V3 is equal to 0. And now this can be reinterpreted as an equation involving the matrix A. And that equation is that A times 1, 1 minus 1 equals 0. Those numbers are the coefficients. It's 1 times V1 plus 1 times V2 plus minus 1 times V3. And then, the fact that this is true means that we have a solution to the homogeneous equation. So the moral is that column relationships really correspond to solutions to the homogeneous equation, and we know that when we do row operations, it doesn't change what the solutions are to the homogeneous equation. So that's why this works. Okay, I know there's a lot going on in this explanation, and it's probably a little bit complicated, but what's important is that the end result is actually quite simple, which is that if we want to find the most efficient description of the image of A, we do Gauss-Jordan elimination, we look at where the pivots are, and we just take the pivot columns, and we take linear combinations or the span of the pivot columns. And it's the columns in the original matrix, not the reduced echelon form. All right, so we spent a lot of time talking about the image of a matrix. What about the kernel? So just to remind you, the kernel of A, which is sometimes abbreviated Ker, is the set of all x such that A times x is equal to 0. Well, what's nice about this is that this is something that you've already been doing. When you solve the equation AX is equal to 0, you're finding the kernel of A. But one thing that's worth pointing out is that one of the ways that we've been describing the solutions to AX equals 0 is actually as a span. So let's go through an example so you can see that. If we look again at the matrix that we were looking at earlier, and now we ask what's the kernel of this matrix? Well, from the reduced echelon form, we can get a system of equations. we have x1 plus x3 is equal to 0, and x2 plus x3 is equal to 0. And we know, because there's no pivot in that column, we can set x3 to be a free variable. So we can set x3 to be equal to t, and then when we plug that into the other equations, we get that x1 is equal to minus t, and x2 is equal to minus t. And so together, we have that the vector x is minus t, t, and we can factor the t out to get t times minus 1, 1. And this description of the space of solutions is a span. Because it's literally the set of scalar multiples of minus 1, 1, that's exactly the span of minus 1, 1. So the point is that we can describe the kernel of A as a span of vectors. In this case, where there was just one free variable, it was a span of a single vector. But if there were two free variables, then it would be a span of two vectors, and so on. Okay, so just to synthesize everything and review, let's do an example of a matrix. In this case, it's a 3x4 matrix, where we want to describe both the image of A and the kernel as spans of vectors. So in order to answer this question, the first thing you want to do is Gauss-Jordan elimination. So I plugged this matrix into Wolfram alpha, and this is what I got. And you can see from this that the pivots are in the first two columns, and so that already allows us to answer the question about what the image of A is. It's just the span of the first two columns of A. So the image of A is the span of 1, 0, 1 and 1, 1, 4. Now, to describe the kernel of A, you have to do a little bit more work, but it's the same work that we've been doing earlier in the class. In this case, because we're talking about the homogeneous equation, AX is equal to 0, we imagine that there's an extra column of all zeros on the right that describes the right side of the equation, and we write out the reduced echelon form as a system of equations. And now in this case, we know that x3 and x4 are free variables, and so we can set them equal to s and t. And then we can solve for x1 and x2. And then combining everything together into a vector again, we get that x can be expressed in terms of s and t, and then we can separate it into a sum of two terms, where one term has an s in front and the other term has a t in front. And then we recognize that this is a linear combination of vectors. Because s and t can be anything, the set of all solutions ends up being all linear combinations of those two vectors. And that's exactly what the span of those two vectors is. So our answer for what the kernel of A is that it's the span of these two vectors, 1, minus 2, 1, 0, and 2, minus 3, 0, 1. So one thing that's worth noting here is that the vectors that are in the image have different dimension than the vectors that are in the kernel. And that's important, because there's a sense in which they live in different places. Even when A is a square matrix and they actually do have the same dimension, you really should think of them as living in different places. So in this case, because A is a 3x4 matrix, you multiply it times vectors that are 4-dimensional, and you get vectors that are 3-dimensional as the output. So A, as a transformation, it's a transformation from R4 to R3. The kernel consists of vectors that live in the domain, which in this case is R4. And so the kernel of A is a subset of R4. Whereas the image of A lives in the output side of the transformation. So the image of A in this case should be a subset of R3. And in general, this is how it works. You think of the kernel of A as being a subset of the domain, whereas the image of A is a subset of the target space. There's a schematic for this that I think is helpful. It's not a literally accurate drawing of the situation, but it's accurate in the same way that a Venn diagram is accurate. If you have a linear transformation T from Rm to Rn, then the kernel of T is a subset of Rm, and it, by definition, consists of vectors which become the zero vector when you plug them into T. So the transformation T sort of collapses the entire kernel down to this single point, the zero vector. And then the image of T is a subset of Rn, and it, by definition, consists of all vectors that you can get by plugging in a vector in Rm into T and seeing what you get on the other side. So T takes all of Rm and sort of squashes it down to become the image of T. And, depending on the transformation, there may be different degrees of squashing that happens. There could be none at all, or there could be a lot. It could be that everything gets sent to the zero vector, and the image of T is just the zero vector. That would be like at the other extreme. So one of the things that we'll be talking about in the next week or so is how do you actually measure the amount of squashing that's happening in this process? And so we'll be talking about that later.